Welcome back. This is on inferences about two means independent samples. This section presents methods for using sample data from two independent samples to do two things: to test hypotheses made about two population means, or to construct confidence intervals or confidence interval estimates of the difference between two means. In part one, we're going to be talking about when the standard deviations are not assumed to be equal. In part two, we'll know when we do know the standard deviations and they're equal. Most of it will be spent on part one, though. So part one, we're going to assume that two samples are independent if the sample values selected from one population are not related to or somehow paired and matched with the sample from the other population. So they're not related or paired. Two samples are dependent if they are paired. And this could be something like a before and after data, if we were doing something on a weight loss drug or a cholesterol lowering drug, or it could be a matched pair such as husband or wife, or even within yourself, left foot, right foot, something like that. The way that you want to see these are these words like dependent, repeated, before and after, matched pairs, and so on. These are the hints that tell us that they're dependent. Determine whether the samples are independent or dependent. To test the effectiveness of Lipitor, cholesterol levels are measured in 250 subjects before and after Lipitor treatments. So I'm seeing that keyword before and after. I'm assuming they're testing each patient and then they're testing the before and the after, and they're using that same patient, so they're somehow linked. And so this is dependent. Part B, on each of the 40 days, the author measured the voltage supplied to his home, and he also measured the voltage produced by the gasoline-powered generator. So the voltage to the home has nothing to do with the gas-powered generator, so we're going to say that these are independent. Let's go over some notation. This is stuff that we've seen before, but because we're doing two means, population mean we know is mu, but we're going to say mu1, population standard deviation, size of the first sample, x bar 1, and S1. Just like when we did for the population proportion, we may call this 1 and 2. We could call this mu f, if I'm talking about like for female, and that sort of thing. So we'll probably use different subscripts, but we just want to make sure we understand that they're different, that they're separated. Some requirements for this is that our sigma 1 and sigma 2 are unknown. We don't know the population standard deviations, and no assumption can be made about the equality. The two samples are independent. Both samples are simple random samples, and they must be sufficiently large and is greater than 30 for both populations. Now, for your assumptions and your phantoms, I'm going to be making sure you check these two. We'll assume that we don't know this because we very rarely know this. And if there is equality, you want to make a note of that when we do the actual test on the calculator, and so that'll pop up in there. But the two things I want you to do are these, and this should seem very familiar to when we did one population means, which we were testing randomness and we were checking that it was bigger than 30, that the sample was big enough. Make sure now that we have to check both samples and both of them have to be bigger than 30 or come from populations having a normal distribution. So let's try one. Remember that we're doing both confidence interval and hypothesis tests, so we need to decide which one we're going to be doing. Number 1, the juniors and seniors compete to see who has the better average on stats tests. 10 randomly selected juniors had an average of 34 points with a standard deviation of 3.9. And the 14 randomly selected seniors had an average of 32.1 points and a standard deviation of 5.2. Assume both populations follow a normal distribution. Is this difference statistically significant using a significance alpha equals 0.05? So this doesn't specifically say do a test or do a confidence interval. Remember, with confidence interval, we're looking for a number. We're trying to find, we're estimating the difference or estimating a standard deviation or doing that. In this case, we're saying, is this statistically significant? So this means that I'm running a test, which means I'm going to be doing phantoms. Let's start with our P. Just like when we did proportions, we're going to have two different things now. So, and we're doing mean, so I'm going to have mu. And the first one I'm going to do is the juniors, so mu sub j. We're going to say mu j is the true mean stats test scores for all juniors. It doesn't say if this is for a specific class. It doesn't say if this is for the school. So we're just going to leave it at that. But if they had addressed that, we'd make sure to do that. And our mu s, we'll say for seniors, same thing but for seniors. Okay. H, our hypotheses. So I have my null and my alternative. And I'm trying to see, is this difference statistically significant? It doesn't say if one is higher than the other, did the seniors do better? It's just saying, is it different? And so this means that I'm going to be testing that mu j is not the same. Is it different than the seniors mu s? And of course, my h has to be equality. This order matters because when you plug it into your calculator and compute everything, that's how we're going to make sure to do is 1 and 2. So make sure that you're plugging in everything appropriately. Let's do our A. So our A said that they were both random. So both samples random. So that checks out. The N1 was 10 juniors and N2 was 14 seniors, or you could say NJ and NS to kind of tie it back into this. We're going to say that they're not greater than 30, but it did say that both populations were following normal distributions. So we'll say populations normal, so that checks out. The name of the test. I'm doing two different means. So I have a 2 sample. It's mean, so I know it's a t distribution, and I'm running a test, so it's going to be 2 samp t-test. Let's go to our calculators. All right, so on our calculators, we're going to stat, test. Here's t-test if I was doing one population. I'm doing 2 populations, so I'm down here at 2 samp t-test. I'm doing statistics, and it's x1, x bar 1, and x2 bar, where this is my first one was my juniors, so let's plug in that. It had an average of 34.0 and a standard deviation of 3.9, and an N was 10. And then the second population was my seniors. Seniors had an average of 32.1 with a standard deviation of 5.2. And the N2 there was 14 seniors. Make sure you're able to find all this information in your notes as you do this and plug it in. We still have more to do. We're doing not equals to, and I'm not going to pool. So for these, because it said the standard deviations were not the population standard deviations, it doesn't say that they're equal, we're going to say not pooled. Let's go ahead and calculate. So I have my t, I have my p-value. Make sure you're getting the same numbers that I am, and I'll meet you back on your notes. All right, so we're back here, and we got our t for test statistic to be t equals 1.0226, and our O obtained p-value to be 0.318. Make a decision, so I'm comparing p-value. Our p-value is 0.318. I'm comparing it to my alpha 0.05. It is definitely bigger than 0.05. P is high, null will fly. We failed to reject the null. So let's go back up here. I failed to reject means I cannot say this. I cannot support this claim that they are different. So I'm going to say there's not enough evidence to say that they're different. So let's do our statement. There is not sufficient evidence to support the claim that the true mean stats test score for all juniors is not equal to that of the seniors. So remember that there's not enough evidence to say that they're not equal. So I'm saying that I can't say that they're not equal. I can't say they're equal, but I can say that there's not enough evidence to say that they're not equal. And we don't have to rewrite the entire second parameter for this one because it's pretty much the same as the juniors, so you can shorthand it in that way. A headline in USA Today proclaimed that men and women are equal talkers. That headline referred to a study of the number of words that samples of men and women spoke in a day. Given below are the results of that study. Assume the study used data from an SRS. Use a 0.01 significance level to test the claim that men and women speak the same number of hours in a day. Is there sufficient evidence to show that women speak more words per day than men? So I'm going to focus, it says test the claim that they're the same, but then it says is there sufficient evidence to say that they speak more? So I'm going to go with that one as my claim instead of just testing that they are the same. So I'm going to do this one instead. So down here, I see that women on average do speak more than men, but remember we're trying to see if is it significantly different? Is it significantly more? So we're testing a claim. Let's go ahead and run RP. So our P is going to be 2 mu's, and I have men and women. So I'm going to start with the men. So mu of the men is the true mean number of words men speak in a day. And my mu W is going to be the true mean, same thing but women, number of words women speak in a day. Okay, so my hypotheses, my null, my alternative, it kind of had 2 different ones in here. It said test the claim that they speak the same. Do women speak more? So I'm going to go with the more one, and I'm going to go here. So I have mu men and mu women. Now, a lot of students would say greater than, right? Because it says more than. But remember, it's asking do women speak more? So if women speak more, it's actually got to be this way. And this all depends, like if I had done women first, right, it would have been women greater than men, or you can reverse these and just write that. Even though we wrote them down like this, we can say women greater than men. Either way, this one's going to be equality. So this depends on what you called this and the order that you did it in. And it also depends on what you plug in to your calculator. So make sure that you're doing these correctly, the way you do it here, and then connect it back to your calculator. Let's do our assumptions. It did say that it was an SRS, and my N for my men was 186, and the N for the women was 210. Both are greater than 30, so that checks out. I have two populations. I'm comparing the two populations, and it's a t-test, so it's going to be 2-SAMP t-test. Go ahead and go to your calculator, and let's plug in this stuff. Okay, so we're going to stat test down to 2-SAMP t-test, or you can just push 4. And I'm trying to put in stats. And my x1 bar, for my x1, we said that x1 was the men. So the population 1 we declared was men. And so that's going to be 15,688.5 with a standard deviation of 8,632.5. And the number was 186. So we're getting this all from the data they gave us. Make sure you're punching in the appropriate places, even though it's not in the order that it's meant to plug in. Our second population was the women, so let's plug that in. And again, it made no difference for this, so we're not going to say that we're going to pool. We'll keep it unpooled. We are testing less than mu2 because the way that we wrote it was men is less than women. And let's calculate. Check to make sure you're getting these same numbers. And if you want to, try doing it the other way. Try maybe doing another test and writing it differently and then plugging it in differently, and you'll still see that you get the same results. Let's go back to our notes and finish up this hypothesis test. All right, so we're back here. Here's my test statistic. Was t equals negative 0.6755. And our O obtained p-value was 0.2499. Make a decision. My 0.25 is definitely greater than the 0.01 significance level it had stated above. And so we're going to say fail to reject the null. So since I'm failing to reject, let's go back to here. This was saying that women talk more. So since we failed to reject, there's not enough evidence to say that women talk more than men. So there's a couple ways that you can write this. I'm going to write it the way that we always have. There is not sufficient evidence to support the claim that the true mean number of words men speak in a day Now, I'm going to do what the alternative says and say that there's not enough evidence to support the claim that the true mean number of words men speak in a day is less than that of women. Now, you could do this because I was doing it following kind of what we've always done is addressing the population here in the parameter, addressing the alternative that we have here, and then tying it in with the it's not there's enough evidence or not enough evidence. Because the question said, do women speak more than men, you could say that you could change this and say there is not enough evidence to support the claim that the true mean numbers of women speak is more than that of men. So you can kind of switch these around to mimic what was said in the question, and that would be fine as well. So part two, if they're known, the sigmas from both populations are known and they're equal, then we're going to say that we want to pool. Let's talk about a couple things in here. If they're both known, they still have to be independent. They still have to be random, and then they both have to be large enough, greater than 30, and or coming from normal distributions. So these are still holding. The only difference is whether I know that their standard deviations are known and or equal, or if I don't. And if I do know that they're equal, then we're going to be pooling. But we never assume that. So let's look at number 3. Assume that two samples are independent, simple random samples selected from normally distributed populations. Also assume that the population standard deviations are equal. So if you look here, let's tag in a few things. It says that they're independent, SRS, normally distributed populations. It says the standard deviations are equal. This tells me that I'm going to have to pool. The mean content from a simple random sample of 25, so that's too small, but it did say it was a normal distribution. So the mean is there, standard deviation of 3.2. The mean of an SRS of filtered, so 25 filtered cigarettes, is 13.2 with a standard deviation of 3.7. We want to test the claim that unfiltered King cigarettes have a mean tar content greater than filtered 100 millimeter cigarettes. All right, so let's go ahead and start RP. And so I have two things. I have the mu, the true mean for the unfiltered, and then I have the true mean for the filtered. So here's my unfiltered king size cigarettes. So we're going to say mu u is the true mean tar content of all unfiltered king size cigarettes and then mu f, let's say mu f for filtered, same thing but for filtered. And this one is for filtered 100 millimeter cigarettes. All right, so my hypotheses, my null, my alternative, it was trying to show that the tar content is greater than filtered. So my mu unfiltered, we want to prove or show or test the claim that it's greater than mu filtered. And of course, my null must be equality. For the assumptions, we have that they are both SRSs. That checks out. Our N for the unfiltered was 25, and the N for the filtered was also 25. So they're not greater than 30, but It does say that the population was normal, so we're okay. The name of the test is again a 2-SAMP t-test. Pause this video, plug in your stuff into your calculator, see if you get the same results that I do. Your test statistic should be t equals 8.0747, and your O should be p equals 8.49 times 10 to the negative 11. If you didn't get that, but you got close to it, go back and check. Did you check that it was pooled? Yes. So make sure that you pooled that. Makes a little bit of a difference. You might still get the same result, but you're not going to get the same test statistic and the p-value. So you want to make sure you're getting those the same. Make a decision. That's times 10 to the negative 11. So I'm moving back my decimal place 11 places. That's really small. So my 8.49 times 10 to the negative 11 definitely is too small. It did not give us an alpha. So we're just going to say 0.05. And so we're going to reject the null. And my statement, we're going to say that there is enough evidence, there is sufficient evidence to support that the mean car content is larger in the unfiltered. So let's start. There is sufficient evidence to support the claim that the true mean tar content of all unfiltered king-size cigarettes is greater than that of filtered 100 millimeter cigarettes. So now we're going to construct a 90% confidence interval for the difference between the two cigarettes as well. So let's do a panic this time. And we've done this before where I had the part A and part B. We just did the parameters and the assumptions up above. So we're going to say same as part A. Even on a test, if I gave you the exact same, then you can just do this. You don't have to write that twice if they're exactly the same. For N, this is going to be a 2 population. So it's a 2-SAMP T interval, so 2-SAMP T int. Go to your calculator. Your information should still be in there. Be sure to pool, because it did say that the standard deviations were equal. You should be getting an interval of 6.2591 to 9.5409. Now, just like we saw when we did two proportions, this is going to make a little bit more complicated than when we just did one population. So this is going to be the mu unfiltered minus the mu filtered. It's doing the difference between, and it's going to be I'm going to round off 1 decimal place, so 6.3 to 9.5. They're both positive, which means in both the lowercase and the uppercase, the unfiltered is higher. So we can see that the unfiltered is higher, even from lower to higher, we can see that's higher. So we're going to say both positive So mu u is larger in both cases. Now, when I do my conclusion, we're going to start off by saying we are 90% confident that the true mean tar content of all unfiltered king size cigarettes is, now we want to say, is it higher or lower? And because they're both higher, we can say 6.3 milligrams to 9.5 milligrams higher than that of all filtered 100 millimeter cigarettes. Remember that when we did, if one of these was negative, then we would have to say that it's either lower, it would be lower than by this much to higher than of this much, or lower than or lower than. So when it was positive and negative, it gets a little trickier. So we want to make sure this is on point when we write down those types of conclusions. We can also say that since 0 is not included in this, that this does say there's a difference. Let's go ahead and write that in. Since 0 is not in our confidence interval, this suggests there is a difference in the two populations, the two population means. And when we did the test, we did see that as well, that there was a difference and that one was actually higher than the other, and we can see that that's reflected in our confidence interval as well.